It's Boris here, back with another computer science video. This one's going to be a little more complicated than the ones I have on my channel. Basically, the lore is that last week I had an interview with a trading firm. For the sake of this video, we'll just say it's a hedge fund. And this was one of the earlier rounds, and they asked me a question which basically revolved around this stream of characters and sort of like a finite stream of characters and registering sequences or registering combinations of characters and kind of returning all the matches for running stream of characters. I wasn't able to find like the exact question, but this is kind of this is a simpler version of it where you just basically return true if you've came across some sequence. I'll explain a little bit better. So like draw IO or sketch IO, I guess. I'll talk a little bit about sort of some ideas that I had. I actually didn't get to the most optimal solution during an interview. So I'm not really sure if I passed or failed yet, but yeah, I did my research and I kind of figured out a way to solve this. So the way this question works is basically if you register something like this is bad, AB, like ABC, and then this is an A. Let's make it lowercase, whatever. Just assume this is like A, B, C. Sorry, I had some lag. And you have a stream of characters where it's like C, C, X, and you have like A, B, C. At this point, you can actually return true because you matched the sequence. And if you have like A, B, C here again, you can at this point also return true because you match the sequence. And you have like, n sequences basically, and you have this stream of characters that just keeps going. And the solution that I kind of quickly came up with, and the one I think we stopped the interview at, was basically something really basic where you have this list of words, and you basically just kind of save them. And then here you also have like a running string. And then here you say something like self.running plus equals letter. So you kind of append the letter to the running street, and then you go through each word. Right, and then you have something like basically if like running minus length of word is less than 0, you continue. Actually, we'll do this, and we basically say if something like self dot running at we'll have like n equals length of self dot running, basically n minus length of word here all the way to n is equal to the word. We return true. So this is kind of like a bad approach where you go through all the words and you try to basically match the tail. You're just trying every combination on the, like for example, if you have like X, I don't know, B, C, A, it'll try this combination here, and then it'll try like this combination here, and it'll basically keep trying different combinations in your registry until you get a match. So if you have no match, and you have like a million words, you go through a million words each query, and you end up returning false. And I believe, let's see here. So, oh, sorry, length, rather here should be n. And I believe this will work, but it'll time out. You'll get a time limit exceeded or something. Which is what I'm betting on. Yeah, so we kind of got through, how many test cases did we get through? Yeah, we got through all the test cases except for the very last one. And the last one failed. Then you could also like make this like a set, right, to like avoid duplicates, but still, this is slow. Yeah, because it goes through every word here. So number of words, and then it does this this substring injection. So this is very slow. And this is kind of where I finished the interview off, and I was surprised I wasn't really asked any follow-up questions about this. But then I came back and I kept thinking about this problem, and I realized there's this data structure, which they don't really actually teach in school, and it's called a trie. Yeah, it's called a trie, which I believe is like a substring from like retrieval. Yeah, so trie. And a trie is basically just a tree where each node has 26 children for like, let's say, lowercase English alphabet. So you kind of start off with like a wildcard, and then you basically have a child for A, you have a child for B, and all the way basically until like Z. Right, so this is B, this is Z, and then some of these are going to be empty. So some of these children are just point to none in Python speak, or null. And then every child that's not none is basically some prefix of the word. And to kind of explain it a little bit better with this example is if we have a word that's like ABC, and then let's say we have a word like ABB, and then we have a word like CAA or something, right? The way a trie for this would look like is you would have your kind of root node, which one goes to A. Would you say A here? Goes to a node, then we have a bunch of nuns, and then we have a C, and then this A here goes to, both of them go to a B. And then the C goes to an A. And then here, one of the B's goes to a C, and then one of the B's goes to a B. So you have a B, and then we have a C, and then we have like this A also goes to an A. So this is, and then here you'd have these like check marks, or like these booleans, which indicate that this is the end of a word. So if you kind of like travel like A, B, C check mark, that means there exists a registration of ABC or ABB or CAA. And when you get to somewhere that has a check mark, that basically means you've completed some word that is registered. And so the lookup on the trie is actually just all of like the length of the word. And the time complexity for the whole program would be basically all of like the longest word would take the longest time, or like all of the number of queries times the longest word versus what we had before, which was like number of queries times like basically the number of like words, like queries times the number of words, basically squared, I think, because then you have to compare the substring, which is like all thing, which is, this is just, or yeah, the query times the longest, the length of the longest word, basically. So it's a lot more efficient. However, this build operation will look a little bit more complicated. So I guess let's jump through the try example real quick. Is you have a node, and then the node has, as we said, let's create an init. Basically, the node has two things. It has the children, which is, you know, initialized by 26 nulls. Then, you know, it has something called the complete, or like is word, which is false by default. And this is basically your node in a try. And so the way this works is we go through each, we create a root, which is just a node, right? This is that like that very kind of first, that very first word. And you go through the list of words, so for like word and words. The tricky part about this is since the stream is running like A, B, you know, C, D, we actually start matching from the last character in this direction. So instead of inserting, if we had a registration like A, B, C, D, instead of registering it like A goes to B, goes to C, goes to D, we actually have to register in reverse order because we start matching in reverse order. We match backwards. So we got to register it as like D goes to C, goes to B, goes to A. That's kind of one of the trick with this question is you kind of have to go through for C in word like reversed. We'll get the value of C, which is just order of C minus order of A, lowercase a. And here we basically say if not, let's get a current. It's going to be our current pointer, self.root. If not, current dot children at cval. This means basically if cval is a null pointer, if we don't already have some, you know, mapping or some prefix that starts with, you know, this particular letter, we're going to create a try node here. So we're going to say cur dot children at cval, you know, equals node, right? And then here we say cur equals cur children cval. So we're actually going to jump to that node, and then from that node we're going to continue creating this. Well, I guess we should call it suffix now because we're going backwards. So if we had like A, B, C, D, it would get mapped to D, C, B, A. And then for each letter, it would kind of create a trie that goes from D to C to B to A, right? And I guess we should actually create the current. So basically, for every new word, we want to start at the very top of the tree. We don't want to just like build a trie that goes like all the way down one branch, right? We always want to insert new words at the top. Cool. So this is kind of the insert method. And then the query is we still have the self running. We can't really get rid of that. So it's always going to be, you know, all of the stream length. So we add the newest letter, and then we start again at the root of the tree, and then we're going to basically say for let's have an I that, or actually we have the n. We're going to loop from the back of the tree. So while we'll do this, while n is greater or equal to 0, we're going to basically say if let's create a cval, which is ord of self running at n minus ord of a, and basically going to say if not cur children at cval. So that means, like, you know, we have this mapping ABCD, but we have something like ABCC as part of our stream, and we don't, our only trie branch starts with a D. We don't have a C. And this is basically what this does, is like if we don't have a branch or a suffix that starts with, you know, this letter, well, we just return false. Otherwise, we can say something like if, oh, I completely forgot to utilize this is word. Basically here, we're going to say cur is word equals true, because at the very end of this thing, where our very last sort of node, we gotta say that this is a word. If cur at any point is word, return true. Here, return is word. So you go through the whole string, and if by any chance basically the branch is equivalent to the whole running stream, we're going to be at the very last node, and so we got to make sure we check the very last node as well. Let's run this. I guess I forgot to subtract n. Rookie move. Yeah, I guess you can probably tell that the interview was a little bit stressful. And wow, it didn't really work. Might have to do it. We're inserting. Oh man, I'm stupid today. I forgot to traverse the tree. I completely forgot to traverse the tree. There you go. Let's see if you get an AC. And there you go. Yeah, I forgot to go to the next value in our suffix, or like to the next character in our suffix. So there you go. This is I believe the optimal solution here, or what I believe to be the optimal solution. This runs in the length of the longest matching. Basically, the worst runtime for this is all of the whole thing, all of running. And the time complexity for this thing is for each word. So number of words multiplied by, yes, the length of each word, or the length of the longest word. And then this here is just all of the worst case scenario, is all of running. And there you go. Thanks for watching this vid.